Lipids are a group of naturally occurring molecules that include fats, waxes, steroids, fat-soluble vitamins, monoglycerides, triglycerides, and phospholipids, to name a few. They're a little interesting in that they are not classified by functional group, but rather by solubility. All of them have very limited water solubility, and that is actually what causes all of these different molecules to be grouped together. They can be extracted from cells by non-polar organic solvents, and that is the extent of their relationship to each other. So this lecture is going to be a little bit odd and not track quite as well by functional group as any of our others has. We're going to be classifying lipids into two groups. One is complex lipids, which are going to contain ester linkages and can be hydrolyzed. So that's a key thing. If you're looking to see if something's a complex lipid, just see if it's possible to hydrolyze it. You can see in the following molecules here, we have an ester linkage here. Well, three of them, here and here. That's a triglyceride. This molecule on the bottom is a wax. You can see there's an ester linkage. So these are two examples of complex lipids. Then you get into simple lipids. They're easy to recognize because in a simple lipid, you do not have an ester linkage. There's no ester linkage, and so you can see right here, we have a steroid on the top and a terpene on the bottom. They are very alkane looking, and that's how you can recognize those. The first thing we're going to look at is a fatty acid. Fatty acids are just carboxylic acids with really long alkyl chains. So they typically have between 12 and 20 carbon atoms in them. And what's interesting is that they contain an even number of carbons, and the reason for that is that sort of their parent is an acetic acid unit. And acetic acid, of course, has 2 carbons. So what we're going to see is even numbers building up by 2. And so what we have with a fatty acid is a carboxylic acid and then just a really long alkyl chain. And we're going to see similar characteristics that we've seen before with all sorts of molecules, that the melting points will increase with increasing molecular weights. The alkyl groups do not have to be saturated, like the example I have up here. They may be saturated or they could be unsaturated. And depending on how much unsaturation or saturation there is, you can end up, as we're going to see in a little bit, with a fat or an oil, which contain fatty acids. So that's going to become important in just a few minutes. Saturated fatty acids don't contain any double bonds. They have a very uniform shape, and therefore the side chain can pack in with neighboring side chains very well. So what we're going to see is these tend to have fairly high melting points. But when you introduce an unsaturation, like with oleic acid, the second molecule, you can see that introduces a kink or a bend. What that does is it causes the side chain to not have the nice uniform shape that the other one did, so it doesn't pack as efficiently, and we see that cis double bonds in particular tend to create low melting points. A trans double bond is still going to have that nice sort of zigzag shape, and so when you have a trans double bond, it has less effect on the melting point. Cis double bonds really introduce some crazy looking kinks though and cause the melting points to go down. We're now going to take a look at fatty acids as they exist in waxes and triglycerides, which are fats and oils. A wax is simply an ester. That is all that it is. It's an ester containing a long chain fatty acid and a long chain alcohol. So, looking at this particular wax right here, you can see that the carboxylic acid part of it, you can see sort of that right there in the backbone, and then looking at the alcohol part, that's right there. So it's just a plain old ester. The only difference with it is your side chain right there for the fatty acid is really, really long, and the side chain for the alcohol is typically really, really long. So they're esters that are solids. They are complex lipids that are water insoluble because of those large alkyl groups, and in general are very hydrophobic, so they function as water repellents. Most natural waxes are protective coats for plants' leaves, insects' exoskeletons, mammals' fur, and birds' feathers. And so that is where they are found a lot in nature, is as a protective coating. Another complex lipid is a class of compounds called triglycerides. Triglycerides are fatty acid esters of a molecule called glycerol. Glycerol is a molecule that is a trialcohol. So if we were to draw it, we'll do it up here in the corner. It is a CH2OH bonded to a CH-OH, and then the bottom is a CH2OH. So 3 carbons and 3 alcohols. Triglycerides, if you take a look at the picture on the right, you can see that glycerol unit that is sitting right there. Right there is that trialcohol unit. Now, triglycerides are the components of fats and oils. Fats, of course, are solids at room temperature, and most are derived from mammals. Oils are liquids at room temperature and tend to come from plants or cold-blooded mammals. Most fats have saturated fatty acids. So you get side chains that can pack together really well, and as a result their melting point goes up and they become solids. And so fats tend to be saturated. Oils, however, have side chains that don't pack together so well. You can see the kinks there, and there. So most oils have unsaturated fatty acids in them, don't pack together so well, and as a result have low melting points, tend to be liquids. So a fat or an oil is basically a triester. You can see here is the glycerol part, right there. That's the alcohol unit. And then attached to it are 3 long-chain fatty acids. So it's glycerol plus 3 fatty acids. It's a triester. And it can be hydrolyzed, and that actually is the process of soap making or saponification. Saponification is defined as the base catalyzed hydrolysis of a fat or an oil, or of a triglyceride. So what you do in a saponification reaction is you take a fat or an oil, and it doesn't matter if it's solid or liquid, so in other words if it's saturated or unsaturated, and you heat it with a fairly concentrated base. When we do this in lab, we use the 50% base that's in the hood. It's the kind of thick, murky looking stuff, and you heat it for about 20 or 30 minutes, and what happens is you hydrolyze the ester under basic conditions. Now when you hydrolyze an ester, if you remember, you get the alcohol. So here our alcohol is actually glycerol, and then you get the carboxylic acid. But the carboxylic acid is in base, and so it is deprotonated. So this is the sodium salt of a carboxylic acid. And that particular molecule that you're looking at there, that sodium salt, is soap. So saponification is nothing more than taking a fat or oil and hydrolyzing the esters. If you examine the structure of a molecule of soap, you can see that there is an ionic end. That's the carboxylic acid that's deprotonated, so it's a minus and a plus. There's an ionic end. And then there's this long chain fatty acid part, and that is a non-polar end. And so that it has sort of a dual nature. It's both polar and non-polar within the same molecule. And that actually causes it to function as a soap and enables it to dissolve grease. So you can see the structure of soap kind of drawn more pictorially instead of as an actual molecular structure. There is an ionic head, that's the carboxylic acid part, and then this long tail right here, that is the non-polar or the hydrophobic end. So let's take a look at how that would want to be arranged. The hydrophobic end clearly wants to avoid water. It wants all those alkyl groups, they want nothing to do with water. The ionic end, though, this is definitely water soluble. It's a salt. And so the way this molecule will orient itself, let's assume that, and let's go to blue for water. Here's blue. Let's assume that out here is a bunch of water. That's all this blue right here. So there's my water. Now the long hydrophobic tail wants absolutely nothing to do with the water. And so those hydrophobic tails cluster around to the inside. Notice that they are actually around each other. They're very much attracted to each other, being the same. Out here, touching the water, is where you have all of those ionic ends, which are water soluble. So by orienting itself in such a manner, a soap molecule, surrounded with other soap molecules, is able sort of to get the best of both worlds. The ionic end gets into the water, and all those little tails stick in next to each other, and they're away from the water and around each other. Now, how this translates into dissolving grease. Grease is, as you're well aware when you've washed your greasy hands, hydrophobic. And so when you have a blob of grease, and that's that yellow kind of blobby looking thing there in the center, a blob of grease is attracted to those hydrophobic tails of a soap molecule. And you can see all those tails are clustered around the grease. The grease, though, offers nothing to the polar carboxylate salt ends of the soap. And so those point away from the grease. So what happens is the grease essentially gets trapped inside all of those tails, leaving the heads out. Now the heads are attracted to the water. So what you get essentially is a little bubble surrounding that grease. So the grease essentially is buried inside this little bubble of soap molecules. That bubble along the outside is ionic. And so the bubble as a whole is water soluble. This bubble thing right here is called a micelle, M-I-C-E-L-L-E. And this micelle, being water soluble, is able to dissolve into water, and when it does, it takes that grease with it, and away it goes. One of the disadvantages of soaps is that they can form soap scums. So if we draw just a very generic soap molecule, we'll just say RCOO minus Na plus. There's a generic soap molecule. If you use a soap in hard water, and that would be water containing calcium ions or iron, well water is a perfect example, or magnesium, any sort of hard water ions. The sodium gets replaced by the other metal ion, And we can draw a new salt where we have RCOO-, and let's do calcium, so we'll have 2 of those to balance it. So there it is. And this would be 2+. Salts, where the soap combines with calcium or iron or magnesium, precipitate. They're not water soluble. That precipitate is known as soap scum. And soap scum can be a real problem. It, of course, will build up on your bathtub. It can build up in your clothes, and just it's not the most pleasant thing. So in the 50s, they developed a very related molecule that did not form scum, and that is a detergent. Detergents are synthetic. Soaps ultimately have their basis in a biological compound, a fat or an oil. Not detergents, though. They're made in a lab, and they are long-chain alkyl benzene sulfonic acid salts. A picture is worth 1,000 words, so go down to this middle structure right here. There's the benzene, there's the alkyl, so that's the alkyl benzene. The sulfonic acid part is right there. You can see that it's very related to a soap. You have a non-polar tail, and then you have a very polar salt-like end to it. So it's going to behave very similarly to a soap. However, when you combine it with the ions that tend to form soap scums, so that would be these guys right here, you don't get a precipitate. So there is no scum. So they do not form insoluble precipitates. We'll just go PPTS, precipitates, with metal ions. So there's no scum. They also, if you're not careful, tend not to be as biodegradable. And they didn't realize that when they first made them. And so people were using them. It was like some miracle, but they weren't degrading in the water systems. And so there was a few years where rivers were foaming and some strange things were going on. But now they've got an idea of what the side chains need to be so that bacteria and enzymes can actually break them down. Phospholipids are a class of lipids that are a major component of all cell membranes. Most phospholipids usually have one phosphoric acid group, you can see that down there at the bottom, and 2 fatty acids. The 2 fatty acids are shown on the top. And then, of course, you can see, kind of hidden in there, the glycerol molecule. So they look very triglyceride-like, only the bottom of it is different. It's actually a phosphate ester, not a carboxylic acid ester. The phosphate will generally have an additional organic molecule attached to it. This particular one has an alcohol attached to it. You can outline it right there. It's called choline, and that actually is fairly common to have that in there. By looking at this molecule, you can see that similar to a triglyceride, we have a non-polar portion, and that would be the 2 alkyl groups. And then looking at, you have a negatively charged phosphate, and here the nitrogen's positively charged. We have an extremely polar end. And as you can probably guess, going to affect how the groups orient themselves in water. When exposed to water, what will happen is the hydrophilic or water attracting head of the molecule, which contains that phosphate group, is going to point out towards the aqueous end. What that will do is that will put the carboxylic acid esters, which are the long chain fatty acids, and that is the hydrophobic end. That will put that pointing out away from the water. So we've got a pretty simple picture here in the center where the circles here are those charged phosphate ends, and then the green squigglies are those alkyl groups on the fatty acid esters. And you could see very kind of micelle-like, the squiggly ends are lined up where they are next to each other and as far away from the water as they can get. the water is, of course, let's go with blue again to be consistent, is going to be out here and out here. That's the water. Taking a look at how it orients itself into a cell membrane, take a look at this picture that's right there. You can see the green squiggly ends pointed to the center, and this red sort of mat is all of those phosphate. This area here is all those phosphate groups that are pointed out toward either side of the membrane, so the water inside the cell and the water outside the cell. So all those hydrophobic tails are lined up against each other away from the water. These lipid molecules essentially serve as a solvent for substances and proteins within them, and the proteins and lipid molecules can diffuse through the lipid matrix, and they can migrate over the membrane from one side to the other. So, in essence, to fill in this blank here for you, cell membranes are a bilayer of phosphoglycerides. So the word that needs to go here is bilayer. Next, we get to steroids. Steroids are one of the easiest things to recognize of the kind of molecules that we'll be looking at. They are polycyclic, and it is essentially 3 6-membered rings fused together. There's 1, there's 2, there's 3, and a 5-membered ring fused at the end. So if we were going to outline the part of the molecule that really makes something a steroid, it would be, and let's go to the right color, there we go. It would be this right here, this whole unit outlined just like that. When you see that, you know something is a steroid. Now we're going to see there are going to be different groups sticking off here and there, double bonds in there, whatever, but you're going to see that basic unit outlined in green in every single one of the examples that we'll look at. So they're polycyclic. The ring junctions are usually all trans. My pen is nice and thick for us. I'm going to adjust that back down a little bit. So the ring junctions are usually all trans, and you can see that. Let's just outline that in red right here. That's trans. And here's a ring junction right there. That's trans. Some common structural features. At carbon number 3, right there, there's carbon number 3, it is not at all uncommon to see some sort of oxygen. It could either be a ketone, so a double bond O, or it could be an alcohol. But when we look at some examples, take a look at carbon 3, you'll notice a ketone or an alcohol. At carbon 17, which is right up here near the top, we're going to see side chains. And they'll vary depending on what kind of steroid it is, but we will see some kind of side chain. And then, also very common, going from carbon number 5, let's put a big red dot on carbon number 5, to either 4 or 6 is typically a double bond. So we'll just put alkene here. So look for a double bond either going there, or if we don't want to do that, let's go ahead and let's just erase that. We could also have a double bond going that way. Okay, not both, just one. Alright, so let's go ahead and let's take a look at some particular steroids that are fairly common. And let's look for those common structural features in those. Our first one is cholesterol. It's got a really bad rap in the news. Everyone's so worried about their cholesterol. But it's actually a really important biological intermediate. You would be in deep trouble without some cholesterol in you. It's a precursor to other steroids. So let's take a look at some of the features that we talked about. One of the first ones would be carbon number 3, there's an OH. Going from 5 to 6 is a C, double bond C. We talked about a side chain at carbon 17, there it is. And then perhaps most importantly, and you can see it just kind of staring you in the face, there is, let's go to green, there is that all-important steroid structure where we have 3 6-membered rings and a 5. You see that? You know it's a steroid. Okay, going to our next one. The sex hormones, testosterone and estradiol. They're kind of interesting. You can see, of course, the basic steroid backbone, the 6-6-6-5, in both of them. You can see, again, that we have some sort of oxygen at carbon number 3. Double bond O is in testosterone, and OH is in estradiol. And there is, in testosterone, a true alkene there between, starting at carbon 5. In estradiol, you can see it's part of an aromatic ring. And then coming off carbon 17, our side chain, so to speak of, is an OH in both of them. So they're very related compounds, but the estradiol is aromatic. Then we bring ourselves to prostaglandins. This is a really broad group of biological chemicals. They serve in your body as biochemical regulators. So they kind of oversee a lot of different biological processes. So biochemical regulators. They'll regulate blood pressure, clotting, allergic responses, digestive activity, labor onset. When someone is going in to have labor induced, they will put a prostaglandin gel on the cervix to kind of get things going. So they are found in many, many biological processes that go on. And of course there are many different kinds, but they are all going to share, yet again, just like a steroid, some common structural characteristics. They're based on a molecule that is called arachidonic acid. And arachidonic acid can be seen down here on the left. It is this molecule right here. So it is a carboxylic acid, has 20 carbons in it. And enzymes will cause the end of it to close off into a 5-membered ring. So what you're going to see is a common structural characteristic of a prostaglandin is sort of an arachidonic parent, but we see a 5-membered ring right there, and then side chains coming off of it, like that. And one of the side chains has a carboxylic acid in it. And then, of course, what's going to regulate their function is the various groups coming off of it. So what you're looking for is a cyclopentane ring with 2 long chains that are trans to each other. Terpenes commonly occur in the oils that give plants their fragrances. Some examples of terpenes are limonene, which is found in the skin of citrus fruits, menthol, which is a peppermint, camphor, which you guys have some experience with, vitamin A is actually a terpene, lemongrass, all sorts of kind of good-smelling plant-like materials. In a terpene, you will find an isoprene unit. So it's composed of 5 carbon isoprene units. The isoprene molecule looks like this below. It's the 5 carbon unit, here, 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 there with a branch. And there is typically, may or may not retain the double bonds in the isoprene unit when it's in a terpene. So here's an example of a very simple terpene composed of 2 isoprene units. And let's go ahead and let's outline the terpene structure. Here is one branch right here. It comes up and over. And let's switch out colors and do the other one. Let's do the other one kind of in a bluish color. Now, the trick is finding the other branch. If you look carefully, the only place where there could be a branch is right here. There's the other branch, the molecule, the rest of the straight chain part is right there. It's pretty typical that you end up where the connection is the head of one of the terpene isoprene units cooked to the tail of the other. So let's go ahead and let's take a look at some different terpenes. Okay, we have two of them down there at the bottom. There's an example of farnesol and limonene. And we'll go through and we'll identify the isoprene units in just a minute or two. But let's go ahead and first classify them. In order to have a terpene, you have to have at least two isoprenes. So the naming of them is based really on a 2-isoprene unit, which is 10 carbons. So we can say that the naming is based on groups of 10. So if you have a pretty simple terpene and it has only 2 isoprene units in it, that means it has 10 carbons. That's like 1 unit. So they call that a monoterpene. Now, jumping up a little bit, let's say you had 20 carbons. That is 2 10-carbon units. So, since it's based on 2 of those groups of 10, it's called a diterpene. Now, say you only had 15 carbons. That's like 1.5. So they call that a sesquiterpene. Sesquiterpene. There are, of course, others as things get larger, and if you ever run into it, you can look up what they are. Now let's go through and find the isoprene units in these two molecules, and then we'll classify them as to monoterpene, diterpene, or sesquiterpene. Alright, so our first one is farnesol, and let's start by just finding the first unit and then seeing that where its head hooks up to another's tail, and so on and so on. So the first part is going to be pretty straightforward. It's right there. And let's switch ink color, and we'll go to the second one. These all just hook up in a line, so it's pretty straightforward. And then we'll switch colors again, and let's go to, I don't know, go to lavender. Here's the third one. So you can see in farnesol that there are 3 isoprene units, and since there are 3 isoprene units, we are looking at farnesol being a sesquiterpene. Alright, now moving on to limonene. Limonene is going to be a little more complicated because you're not just hooked straight in a line, tail of one, head to another, all in a line. So what I typically try to do is I try to find that kind of isopropyl-like branch, and so that is going to be that right there. And I'm going to come out and I'm going to identify my first isoprene unit. Now I have to go one way or the other to get that 5th carbon in, and I'm not quite sure which way, so I'm going to choose one. If I choose incorrectly, it will become obvious, and I can erase and start over. So I'm just going to go up that way. So that means my next unit is going to be hooked to that. Since I've gone to sort of the head of the molecule right there, I better have that branch tail hooking up to it. And lo and behold, there it is. There's the branch right there, and then coming down like that. So hidden within limonene are 2 isoprene units. It's 10 carbons, so it's 1 10-carbon unit. Limonene is a mono. Let's get to black. There we go. It's a monoterpene. Okay, that pretty much sums up lipids. So review the chapter, and the test isn't really going to be anything more complicated than what you've seen on here.